Hi students, welcome to the chapter of number systems. As we all know, natural numbers include 1, 2, 3, 4, 5 and so on upwards up to infinity, and whole numbers include 0 in addition to natural numbers, and integers include, in addition to 0 and natural numbers, all negative numbers -1, -2, -3, -4 downwards up to infinity. Now the fractional number is in the form of p by q, where q is not equal to 0. Now there are two decimals, one can be terminating, one will not be terminating. If the decimal expansion is not terminating, non-recurring, then it is an irrational number. If the decimal expansion is either terminating or non-terminating but repeating decimal, then it's a rational number. There is a formula to find whether the rational number is a repeating decimal or terminating decimal. So that formula is p by q, where p and q are co-prime numbers, where the denominator q is in the form of prime factor 2 to the power of m multiplied by 5 to the power of n only, then the decimal expansion is terminating. If the denominator q is in the form of any other prime factor, 7 to the power of 1, 11 to the power of 1, or 2 to the power of m, 5 to the power of n, multiplied by 3 to the power of n, then the decimal expansion of that fractional number is not terminating but repeating decimal. Now, there is a difference between prime numbers and co-prime numbers. Prime number is one which is divisible by itself and common factor 1. And any two pair of prime numbers are co-prime numbers. But co-prime numbers can include more than two numbers where common factor is only 1. So it could have 3 or 4 or 5 numbers where the common factor of all those numbers is 1 only, then all those numbers are co-prime numbers. Let us now look at some of the examples here. Two important properties are associated with positive integers. One, fundamental theorem of arithmetic related to multiplication. Two, Euclid division algorithm related to divisibility. Euclid division lemma is based on the equation dividend is equal to divisor multiplied by quotient plus remainder, where A is dividend, B is divisor, Q is quotient, and R is the remainder. It is used to find HCF of two positive numbers only. So let us take, for example, numbers 225 and 135. Let us take the large number as dividend, that is A, and the smaller number as the divisor, that is B in the formula. Step 1, 225 is equal to BQ plus R, that is 225 is equal to 135 multiplied by 1 plus 90. So here we get the remainder as 90. Now this 90 becomes the divisor in the next step. And the previous divisor becomes dividend in step 2. That is 135 is equal to 90 multiplied by 1 plus 45. Now the remainder is still not 0. It is equal to 45. Then in step 3, divisor of step 2 becomes dividend of step 3. 90 is equal to 45 multiplied by 2 plus remainder is equal to 0. When the remainder becomes 0, the operation stops. Here the divisor of the last step, 45, becomes the HCF. When Euclid division lemma could find HCF of only two numbers, we can find HCF of multiple numbers by common division method. HCF of 245, 575, 625 and 155 can be found by the common division method. Here 5 is a factor of all, and in the first step it divides 245, 575, 625 and 155. In the second step, 5 is not a factor of 49 and 31, and in the third step 5 is not a factor of 49, 23 and 31. Therefore, the HCF of these numbers is only 5. HCF is defined as the product of the smallest power in each common prime factor involved in the numbers. LCM is defined as the product of the greatest power of each prime factor involved in the numbers. Between 6a to the power of 4, b to the power of 7, c to the power of 8, and 3a to the power of 2, b to the power of 6, c to the power of 4, the HCF is 3a squared, b to the power of 6, and c to the power of 4. And the LCM of these two numbers is 6a to the power of 4, b to the power of 7, and c to the power of 8. Now, the HCF of two numbers a and b and LCM of two numbers a and b, the formula is the product of these two numbers a multiplied by b must be equal to HCF of ab multiplied by LCM of a and b. Therefore, between 135 and 225, these two numbers, 45 is the HCF of these two numbers, 675 is the LCM of these two numbers. 45 multiplied by 675 is the same as 135 multiplied by 225. So, HCF of A and B is equal to A multiplied by B by LCM of A and B. Which of the following numbers is not a perfect square? 1296. It is divisible by 2 and 3. It has got two pairs of 2 and two pairs of 3. So we take 2 multiplied by 2 multiplied by 3 multiplied by 3 is the HCF of 1296. That takes you to 36. In the next problem, 46305, it is a factor of 3 to the power of 3, 5 to the power of 1 multiplied by 7 to the power of 3. The prime factors involved in this number are not in pairs of 2. It is not a perfect square. And in the case of 2310, none of the prime factors involved in these numbers are in pairs. So this 2310 is also not a perfect square. The cube root is prime factorization method where the prime factors appear in pairs of 3. How many numbers are there between 11 squared and 12 squared? Let A be the smaller number, B be the larger number. If B is the larger number 2, 2B is the numbers that appear between 11 to the power of 2 and 12 to the power of 2. Try this method with any numbers. And 35 squared, if the unit digit is 5, is got by this formula. Let the first digit 3 be A, second digit 5 be B. A multiplied by A plus 1 multiplied by 100 plus B squared, 1225 is the answer for 35 squared. Try this with 65 to the power of 2, that is 4225. 75 to the power of 2 is 5625. This formula can work out for larger numbers as well. Let us take 14,345 to the power of 2. Let the first 4 digits be A, that is 1434, and the next unit digit be 5. Therefore, 1434 into 1435 into 100 plus B squared is 20,57,79,025. As you all know, a prime factor has only two factors, that is 1 and the number itself. A composite number has more than two factors. The lowest composite number is 4. 0 and 1 are neither prime nor composite. Now, you must understand that prime number and co-prime numbers are not the same. Co-prime numbers could be any two prime numbers which do not have a common factor other than 1. But now, co-prime numbers can consist of more than two numbers, but there is no common factor in them other than 1. For example, 14 and 15. 14 is 1 multiplied by 2 multiplied by 7, and 15 is 1 multiplied by 3 and multiplied by 5. There is no common prime factor in these two numbers other than 1. So 14 and 15 are co-prime numbers. But 14 and 21 are not co-prime because 1 multiplied by 2 multiplied by 7 is equal to 14 21 is equal to 1 multiplied by 3 multiplied by 7 is equal to 21. So it has 7 as a common factor apart from 1. So these two are not co-prime numbers. Whereas 15 and 8 are co-prime numbers because 1 multiplied by 3 multiplied by 5 is 15, 1 multiplied by 2 multiplied by 4 is 8, and it has no common factor other than 1. Therefore, 8 and 15 are co-prime numbers. Now you will have problems where you will be asked to prove root 5 is a rational number. Let us assume that root 5 is a rational number. Then it must satisfy the equation P by Q is equal to square root of 5, where P by Q are co-prime numbers having a common factor as 1 only. Squaring both sides, we get P squared by Q squared is equal to 5. That makes P squared is equal to 5Q squared. The equation proves P squared is a multiple of 5. P squared is divisible by 5, therefore P is also divisible by 5. Let us now assume P is equal to 5C. Then substituting P value in P squared is equal to 5Q squared, we get 5C squared is equal to 5Q squared. 25C squared is equal to 5Q squared. Divide both sides by 5. Then you get 5C squared is equal to Q squared. It means that Q squared is also a multiple of 5 and must be divisible by 5. So it means that P and Q share a common factor 5 other than 1. In order to be a rational number, P by Q, both P by Q are co-prime numbers having 1 as a common factor. It contradicts our assumption that P by Q is a rational number and therefore root 5 is irrational. Now let us see the other problems as well. Prove that 7 root 5 is irrational. If we assume 7 root 5 is rational, then P by Q must be equal to 7 square root of 5, where P and Q are integers. This gives P by 7Q is equal to root 5. Since P and Q are integers, P by 7Q is rational on the left hand side, but root 5 is irrational on the right hand side. This contradicts the fact that our assumption 7 root 5 is a rational number. Therefore, 7 root 5 is irrational. The next problem, prove that 6 plus root 2 is irrational. Assume 6 plus root 2 is rational. Then P by Q must be equal to 6 plus root 2. Then root 2 is equal to P by Q minus 6. Since P by Q are integers and 6 is also an integer, it is a rational number on the right hand side, but root 2 on the left hand side is irrational. This contradicts the fact that our assumption that it is a rational number. Therefore, 6 plus root 2 is irrational. Prove that 2 root 3 plus root 5 is irrational. If we assume 2 root 3 plus root 5 is rational, P by Q is equal to 2 root 3 plus root 5. Squaring both sides, P squared by Q squared is equal to 2 root 3 plus root 5 whole squared. Then apply A plus B whole squared formula. Then it becomes P squared by Q squared is equal to 17 plus 4 root 15. P squared by Q squared becomes 17 plus 4 root 15. Also, P squared by Q squared minus 17 is equal to 4 root 15. Then P squared by Q squared minus 17 by 4 is root 15. On the left hand side, all are integers, which is a rational number. But on the right hand side, which is irrational, our assumption is wrong. Therefore, 2 root 3 plus root 5 is irrational. Coming to the last problem, 5 by 2 minus root 3 is irrational. If the denominator has an irrational number, we have to rationalize the denominator. 2 minus root 3 is the denominator. So we have to use the formula a plus b into a minus b to get it as a whole number. Therefore, 5 multiplied by 2 plus root 3 divided by 2 minus root 3 into 2 plus root 3 gives us 10 plus 5 root 3 as the answer. Now assume P by Q is equal to 10 plus 5 root 3. P by Q minus 10 becomes 5 root 3. then P by Q minus 10 divided by E is equal to root 3. This contradicts our assumption that 5 by 2 minus root 3 is irrational, because on the left hand side we have a rational number, on the right hand side we have only root 3. This contradicts our assumption. Therefore, 5 by 2 minus 3 is irrational. Thank you.